Alright, so after we analyze our video in Logger Pro, we now have some data points, and we can use those points in our graphs um, to conduct our experiments. So the first thing we're going to look at is projectile motion. Okay, so let's go ahead and click on to our Logger Pro graph. Alright, so for this particular demonstration I used clip 14. I can use any clip. I just chose to use 14. Let's start from the beginning so you can kind of take a look at it. There's my clip. Alright. So from this clip we get our graph. And before we look at our data, what are we looking at here? In projectile motion, we know that, or what we're trying to prove, that there's little to no acceleration in the x direction. The acceleration in the y direction is due to gravity, which is at a constant rate of negative 9.8 meters per second. We also want to look at the path of the ball in terms of x and y coordinates. So to do that, we have our graph of position here. Our x coordinate is in the red, and our y coordinate is in blue, and their positions based on time. Time is our x-axis. So to get a good fit, we're going to go to Analyze. For our x coordinates, we're going to analyze linear fit because it's a line. Video analysis x. Go ahead and analyze that. Look at this later. Now for our y coordinates, we're going to analyze curve fit. Video analysis y. Okay. Now this is a little more complicated. You can see on the screen that the shape is that of a parabola. So in our general equations, we want to select quadratic because quadratic equations are going to yield a parabola. So we're going to try our fit. You can see the fit looks good. So we're going to say okay. All right. Okay. So now from our graph tells us a few things. We know from physics that the derivative of position is velocity, and the derivative of velocity is acceleration. And we also know from physics and calculus that in looking at a graph, the value of a derivative is the slope of a tangent line. So the slope of the graph is the derivative at a certain point. So we're going to begin by looking at the x coordinates. So we're talking about the x dimension. Our linear fit tells us the slope of our x coordinates is negative 3.152 meters per second. So the derivative of the x position is negative 3.152 meters per second. That means that the velocity, therefore, the average velocity of the ball as it moves through the air is negative 3.152 meters per second. Let's look at our data table to see if this is true. And if you look at the x coordinates for velocity, you can see that while they do change, they are all very close to negative 3.152 meters per second. And the slight discrepancies in values here are based on somewhat inaccurate clicks. You can see that they're not all in line. When I was clicking in the previous video segment, you could see that I wasn't always in the exact same spot. It's very hard to do that. And also, there is a bit of air resistance acting in the x direction, but that's very minimal. And so you can see that our first assumption that there is no acceleration in the x direction holds true here. There's little to no acceleration, as the velocity in the x direction is an average of negative 3.152 meters per second. The second thing we're going to look at is acceleration in the y direction. We know that the only force, once the ball is released from my hand, the only force acting on the ball is that of gravity. And the universal the acceleration due to gravity is negative 9.8 meters per second. So therefore, our graph, this parabola, the velocities in the y direction should be changing at a rate of negative 9.8 meters per second. So if we look at our graph of y coordinates, you can see it's a parabola. And let's look at approximately about 2.1 seconds when the ball is released from my hand. You can see that the slope at this point, the tangent line here, the slope of the tangent line is very steep and is positive and very steep, which means the velocity is great. And if we look at our data table, it's clear at approximately 2.1, 2.2 seconds, our velocity is the greatest it will be in the y direction. Now, after this point, as the ball continues to move in its flight, you can see in the data table that the velocities gradually decrease, and they do so at a rate of very close to that of negative 9.8 meters per second. And if you look at our graph, you can see that the slope of the tangent line here at approximately 2.5 seconds is a lot flatter, a lot less steep, still positive but less steep than it was at 2.1 seconds. And if you look at approximately 2.7 seconds, between 2.7 and 2.8 seconds in this area here, you can see that the slope of the tangent line is flat, which means the velocity has now approached, the velocity in the y direction is now 0. And that's indicated here on our graph. You can see that these data points are approaching 0 and now have approached 0 between 2.803 seconds and 2.837 seconds as it switches from positive to negative. That means that within this time frame, between 2.7 and 2.8 seconds, the ball has reached its maximum height. As it is no longer rising, it is now beginning to fall. And that's indicated by the negative velocities in the y direction. And you can see that in looking at the data table and also in looking at the graph of our y coordinates. You can see that from this point on, the slope is now negative, the slope of the tangent line is negative, and is gradually getting steeper and steeper.